listeners, let us start our new session of Chapter 14, Oscillations. Now let us understand force law for simple harmonic motion. Here we know the Newton's second law, which is related with the force and the acceleration. And in earlier topic we have already understood the acceleration of a particle in a SHM system. So based on the Newton's second law, we are having F equal to ma. Now here, this force, that is a function of time, because we are talking about a simple harmonic motion, which is a periodic motion. And periodic motion, while we are talking about, this is always depending on the time. So we are having that equation f of t equal to ma. And acceleration equation which we have derived earlier, that is minus omega square x of t. By substituting that value in force equation, we are getting that value f of t equal to minus m omega square x of t. Now let us substitute m omega square by the constant k, which is known as force constant. So k equal to m omega square. By making the subject of formula omega angular frequency, we are getting that equation omega equal to under root of k by m. Here, whenever the object is available initially at a mean position, that is at the rest condition, and force onto the object would be 0. Now when the object starts to displace from its mean position, it develops a restoring force and try to move towards its mean position, equilibrium position. So here this force is always directed towards its mean position in the opposite direction of the displacement, and that's why over here negative sign is predicted for the force equation based on its direction of force opposite with respect to the displacement. So here this restoring force is developed onto the object, which provides the simple harmonic motion. Earlier we have defined the displacement equation x of t equal to a cos omega t plus phi. And here the force equation we are having minus k x of t. So here, while we are taking displacement towards the force, that derivation while we want, then we want to differentiate the displacement equation 2 times and be able to get force equation. An opposite process we need to perform. By integrating the force equation 2 times, we able to get displacement equation x of t. Here by focusing that equation of the force, it defines that force is linearly proportional to x of t. Here a particle is oscillating from its mean position due to this developed restoring force, which generates the SHM, linear harmonic oscillator. Here we are taking proportionality only x of t, means x raised to power 1. Here we are avoiding another components x square or x cube. This x square and x cube terms are, if available, then it will give you the non-linear oscillators, and it won't be available further as a SHM. So for the SHM, we are always focusing on a linear harmonic oscillator with single frequency variation. Let us understand example regarding the same. 2 identical springs of spring constant K are attached to a block with mass M and to fixed supports as shown in a figure over here. Show that when the mass is displaced from its equilibrium position on either side, it executes a simple harmonic motion. Find the period of oscillations. So here what will happen? While the mass is displaced from its mean position with the distance x, for example, from mean position it is moving towards the right direction. So here, under this condition, the first spring will elongated by the length of equal to x amount of displacement, and by the same amount the another spring that is compressed by the same amount of length. So here the force is developed onto both the spring. Here we can see the diagram that first spring is elongated and second spring is compressed by the same amount x distance and x length. So here by that elongation and compression, the force is exerted onto the object, onto the mass m, because as the displacement is arised, restoring force is developed onto the object. So due to that moment, F1 force is exerted by the spring onto the left side, which is pulling the mass towards its mean position, that F1 equal to minus kx. And another force F2 is developed from another spring due to the compression, and it is pushing the block towards the mean position in opposite direction of displacement. So F2 is again generated minus kx, because F1 and F2 both are generated in the opposite direction of displacement, so both are negative. So here we can say that F1 equal to minus kx and F2 is also equal to minus kx. Individual force we have calculated. Now by using the superposition law, the total force, the net force acting onto the mass, that is F equal to F1 plus F2, that is minus kx will give you minus twice kx. So force acting onto the mass, which is proportional to the displacement, and it is directed towards the mean position, defines with the negative sign on the force equation. So here the time period of oscillations is defined by t equal to 2 pi under root m twice k. We know the time period of oscillations for the spring, actually t equal to 2 pi under root m by k. But here instead of k, we are getting twice k due to two springs. So here that time period of oscillations we are having t equal to 2 pi under root m by twice k. Now let us understand energy in simple harmonic motion. In simple harmonic motion, we are going to focus in total mechanical energy of the object. Total mechanical energy covers the kinetic energy and potential energy of a particle. So here, let us understand first individual energy component, and then we are going to add both the values to get a total mechanical energy of the particle of the object. Kinetic energy, first let us understand that we know its kinetic energy equation k equal to 1/2 mv square. V gives you the velocity of the particle or object. Earlier we have already derived the equation for velocity or speed, that v equal to omega a sine omega t plus phi. Let us substitute the value of velocity over here. So we will get kinetic energy k equal to 1/2 m omega square a square sine square omega t plus phi. Now in earlier topic in the force law for simple harmonic, we have substituted m omega square by k value, which we are replacing again. So this kinetic energy k equal to 1/2 k s square sine square omega t plus phi. Here the v is the velocity of that is a periodic function with respect to time. It is 0 when at the extreme position of the displacement, and kinetic energy, which is a periodic function of time. This kinetic energy is 0 when displacement is maximum, and this kinetic energy is maximum when particle is available at its mean position. Now, let us understand potential energy. The potential energy that is possible for conservative forces only. We know the spring force, which we have calculated, F equal to minus kx, which is a conservative force which associated with the potential energy. So this potential energy we are having 1/2 kx square, and x is the displacement amount of the particle. We know that equation x equal to a cos omega t plus phi. So substitute that displacement equation in potential energy. So u of x, that would be equal to 1/2 ks square cos square omega t plus phi. Here we are having the time period t by 2. This potential energy is 0 at a mean position and extreme at a maximum displacement, which is the opposite function with the kinetic energy. So while we are combining potential energy and kinetic energy to get the total mechanical energy of the particle or object, we will get E equal to total energy E equal to U plus K, potential energy plus kinetic energy. Let us substitute the derived equation for potential energy and kinetic energy over here. That 1/2 K square cos square omega t plus 5, the potential energy, and 1/2 K square sin square omega t plus 5, the kinetic energy. And solve it, and we are getting total mechanical energy E equal to 1/2 K square. So here this total mechanical energy of harmonic oscillator, which is independent of the time for motion under any conservative force, it justifies that at any instant of time, total mechanical energy will remain constant. If potential energy gets decreasing, then by the same amount, kinetic energy is increases. And if kinetic energy is decreases, then potential energy is increases. Ultimately, its a net energy, total energy value will remain constant. Let us understand this thing by the diagram. Here we are having first diagram energy time consideration. Here a black line justify for the potential energy variation, and kinetic energy denoted with the black line. So potential energy equation we are having in terms of cos and cos square omega t plus phi, and kinetic energy we are having in terms of sin square omega t plus phi. So here the cos and sin function will be represented, and that will give you the sinusoidal function of both the value. But ultimately the net force while we are calculating, it justified with the straight line as it is noted E equal to K of t plus U of t. So here by that small portion of the waveform which is denoted over here as a diagram B, in which the kinetic energy while increases, that potential energy gets reduces. At mean position, we are having kinetic energy maximum and potential energy 0. Then after, again potential energy gets increases and kinetic energy gets reduces. Ultimately, it's a net effect. The total energy remains constant. Let us understand the example regarding the same. A block whose mass is 1 kilogram is fastened to a spring. The spring has a spring constant 15 Newton per meter. The block is pulled to a distance 10 centimeter from its equilibrium position x equal to 0 on a frictionless surface from rest at t equals to 0 time instant. Calculate the kinetic potential and total energy of the block when it is 5 centimeter away from its mean position. So here, let us first define the displacement amount and calculate its radiant frequency. So we are having angular radiant frequency omega equal to under root k by m. The force constant k is given 15 Newton per meter and mass of the object is given 1 kilogram. By substituting those values, we are having omega, that is a 7.07 radian per second. We are having x of t, that is a cos omega t plus phi. Here we are taking the phase difference phi 0. So a cos omega t. This is what the displacement equation we are having. A, the displacement amount is given 10 centimeter initially. So that 10 centimeter is converted into meter, and we can substitute A equal to 0.1 meter into cos omega, that is 7.07 into time t. Now, when the particle is 5 centimeter away from its mean position, then x of t that we are having 0.05, that 5 centimeter is converted into meter, that we can substitute as 0.05 meter. X of t that would be equal to 0.1 a cos omega 7.07 into t. By solving that equation, we are having cos omega t that would be equal to 0.5, and sin omega t we are having root 3 by 2. Now, let us calculate its velocity at x equal to 5 centimeter. We are having a velocity equation v of t equal to omega a minus omega a sin omega t. And sin omega t, which we have already calculated, that is root 3 by 2. So here, while substituting that value a omega sin omega t, that we are getting that equation v of t equal to a omega sin omega t. That a is 0.1, omega is 7.07 into sin omega t. That we are getting 0.61 meter per second velocity of that object. Now, kinetic energy equation, we are having 1/2 mv square. Substitute the value of mass of the object 1 kilogram, and velocity we have calculated 0.61 meter per second. By substituting those values, we are having kinetic energy 0.19 joule. Potential energy equation, we are having 1/2 kx square. So 1/2 k, the constant force constant value is given 15 Newton per meter, and x value we have calculated just before that, that is given 5 centimeter, it means 0.05 meter. By substituting those values, we are having potential energy 0.0625 joule. Total energy equal to kinetic energy plus potential energy. By adding those values, we are having the total energy 0.25 joule. So here, the maximum displacement of is available at the time the kinetic energy is 0. So the total energy is available by its potential energy only. So at that time, the total energy we are having by maximum displacement, that is 10 centimeter, it means 0.1 meter. So at that time, total energy equal to potential energy, and potential energy equation we are having 1/2 kx square. At that time, x we supposed to take a maximum displacement 10 centimeter. So by substituting those values, we are having its a total energy 1/2 kx square, that is a 0.25 joule. So here again we are getting the same value of total energy, which defines that its a total energy remains constant and follow the conservation law of energy. Clear? Here we are going to end the session. Hope you understood. Thank you.